Hi there, my name's Wally Akbari and I'm a Principal Solutions Architect working at AWS. Today, I'm going to take you through a few slides, an example scenario, and then a demo to show you how you can use Amazon FSx to power your data-dense and high-performance Amazon EKS workloads, such as machine learning and training, generative AI and inferencing, to analytics and so forth. Now, if you think about it, when you're building a new application, you think about the Amazon EC2 compute type that you select to power your workload to get the performance and cost that you're looking for. Now, it's also really important to think about the optimal storage service that you're going to pick for your application as its persistent data layer. So you get the performance and cost you're looking for. And, when you start thinking about operating at scale, you really want your storage layer and the storage service that you pick to, give you the operational efficiency at scale in your architecture as you start to scale to hundreds and even thousands of pods. Now, let's look at a high-level diagram. Okay, this is a very high-level diagram of a generative AI chatbot deployed on Amazon EKS. We can see we've got the Amazon EKS orchestration layer, then we've got the AWS accelerated compute layer, and you'd pick which type of AWS accelerated compute you'd use to power your VLLM inferencing engine in there. And then importantly, you see down the bottom where the storage layer is, right? And that's where you need to think about, okay, which storage service and which storage architecture should I use to also give me the performance and cost and operational efficiency I need, for example, for this generative AI application chatbot use case. Now, we have a few storage services that support the CSI driver, the EKS CSI driver, from Amazon FSx for Lustre to Amazon FSx for NetApp ONTAP to Amazon FSx for OpenZFS, and also Amazon EFS. Now, I'm not going to dive into these today. What I want to show you was a summary at a glance table where if you look at it at a high level, all these storage services, these AWS storage services, give you really awesome performance. And they also provide you with single AZ and multi-AZ capability for deployment to meet your application's resiliency requirements and performance. So, if they all give you awesome performance and capability, which one do you select for your different Amazon EKS use cases? Well, start off with your use case, which I've kind of given you guys a guidance about as option one up the top. Start off with use case. And then look at the data services that each of these different services provide and figure out, okay, which one of these data services do I need? For example, if you're starting off with a machine learning use case or a generative AI inference use case, maybe have a look at Amazon FSx for Lustre, especially if you have data that you need to integrate with that's stored in Amazon S3. So for example, when you spin up your pods, you need to access lots and lots of data from Amazon S3. Well, maybe look at Amazon FSx for Lustre. It has native Amazon S3 integration. What that means is when you create a persistent volume that's backed by Amazon FSx for Lustre, you can have it directly linked to an Amazon S3 bucket for data imports and exports. Now, that's pretty awesome. No code required to integrate with your data lake data. I'm going to show you a demo of that in a few minutes. So, we talked about AWS storage services in the previous slide. These are what we call shared file services. These are fully managed services. So you basically spin it up and use it. It's fully managed for you. So there's two models that our customers deploy their persistent volumes in. One is where they deploy a single persistent volume or a PV for each EKS pod deployed. Now, this is great when you're operating with a few pods or a small volume of data. And there's considerations around performance and capacity utilization when you deploy a single PV for every single pod they deploy. And these could be very small PVs as well, right? And that can all add up in terms of size and cost, and especially if you're not using all the storage within a PV and you're pre-provisioning it. Now, one other method that our customers use to get operational efficiency and more performance is by using a shared persistent volume model where they deploy a single Amazon FSx or EFS instance, create a persistent volume from that on the EKS cluster, and then have lots and lots of pods bind or bound to that single PV. What that means is you could spin up a very large a large FSX instance, or have a large EFS instance, and you get the aggregated performance of that entire instance for your hundreds or thousands of pods versus creating little PVs and assigning to each of the pods. Secondly, you would inherit the cost optimization capabilities of each of the services. For example, FSX and EFS have tiering capabilities. That's pretty awesome. A great way to save data when you're tearing down inactive data. And obviously, when you think about it, deploying thousands of pods doesn't mean you need thousands of persistent volumes, right? Allow for operational efficiency in your architecture by leveraging shared Amazon EFS or FSX file services in your architectures. Okay, let's put all of it together, right? Let's go through an example scenario before I take you through a demo to show you how to actually configure Amazon FSX for Lustre with your Amazon EKS cluster and pods. Okay, imagine you're building a generative AI or ML workflow on Amazon EKS, and you have thousands of pods that access the same models or training data. Which storage service do you choose? Now, before we go into which one, let's look back at the two models, right, that we talked about. Customers deploy a single pod and a single PV to each pod approach. So in this scenario, imagine it's an inference scenario, and you have a model repository, and you deploy pods to use their own provisioned PVCs. So each pod spins up, and this, could have a large container image with a model embedded in there as well, which you want to try to move away from and have a decoupled architecture for obviously performance and scale. But let's say they deploy a pod, each one gets its own PVC. The next step is, a model is copied from somewhere, a model repository. That time to copy the model data into each PVC can take time, okay? And then the model data needs to be loaded from the PV that's attached to each pod into the GPU memory. Then you can start inferencing. So that's a few hops before you can actually start inferencing, and that can affect your, obviously, pod latency and pod startup time, and also time to inference and time to first input and output token, right, for your app. Now, what if you use the shared storage approach using Amazon FSX for Lustre? And let's say your models and your model repository were stored on Amazon S3. So have all your models on Amazon S3, you spin up an FSX for Lustre file system, and during deployment, you link it to the Amazon S3 bucket with a simple configuration, give it the bucket name and some parameters of whether you want to import and or export changes between the file system and the S3 bucket. So you spin up an FSX for Lustre file system, point it to the S3 bucket. Now notice you haven't deployed your pods yet, all right? We don't want to waste really important GPU cycles yet. Now the file system is up and running, the FSX for Lustre file system's up and running, you go and deploy your pods, and you basically point them to use the same FSX for Lustre persistent volume. So you can have thousands of those pods access the same model cache effectively. Now, the model that you're storing on Amazon S3, it can either be pulled into the FSX for Lustre instance, or you could pre-warm the FSX for Lustre instance before you deploy your pods. So that way, when your pods are up and running, they have immediate access to the model data, and it gets loaded into GPU memory. And one of the benefits of using Amazon FSX for Lustre for inference, and in particular for machine learning scenarios, is that it supports NVIDIA's GDS capability, where you have basically direct memory load from direct data load from the file system into your GPU memory through EFA, our Elastic Fabric Adapter capability, which is really awesome, right? To even give you high throughput, high performance, and decrease that data load time into GPU memory. Okay, we've talked a lot about using Amazon FSX for Lustre and its benefits for data dense and high performance Amazon EKS apps. Let's dive into a demo to show you how easy it is to configure, and we'll also look at the awesome S3 integration capabilities. I'm going to show you how you can configure and use an Amazon FSX for Lustre file system as a persistent volume within an Amazon EKS cluster using the CSI driver. I'm also going to show you the benefits of using FSX for Lustre's native Amazon S3 integration, which allows you to set up automatic import and export of data between the FSX for Lustre file system and an S3 bucket that is linked to. This allows for the FSX Veloster file system to act as a high-performance cache for hot data stored in an S3 bucket. For high-performance use cases, such as machine learning and training, where you could have hundreds or even thousands of pods that need access to the same training data, wouldn't it be awesome if you could attach the same persistent volume, such as an FSX Veloster file system, to all your pods, and have a shared high-performance volume that stores your training data or hot assets? Okay, let's start the demo. Let's install the CSI driver for the FSX Veloster service on an EKS cluster that has 2 compute nodes. First, we need to create an IAM policy that will allow permissions to operate with the FSX Veloster service. Let's create an EKS cluster service account that uses that IAM policy we just created. Now we're ready to install the CSI driver, where it will install the package from the GitHub repository. As you can see, the CSI driver will deploy 2 sets of pods on each EKS cluster node. We are now going to create a persistent volume using a YAML file definition. In order to do this, we need to get the details of the FSX Veloster instance that our admin has already provisioned for us. So we'll go to the Amazon FSX console and get these details. Let's look at the instance details. We can see that this is a 1.2 terabyte FSX instance. We are going to copy the values that are highlighted, such as instance ID, storage capacity, mount name, and the DNS name, and use them to create our persistent volume definition file. I have created a persistent volume definition already, where I have given the PV a name of FSX-PV, and also copied across the FSX instance values we noted earlier. Let's go ahead and create this PV definition. We can see that the PV has been bound. Now let's create a persistent volume claim definition to the FSX-PV we just created, so that we can use the FSX Veloster persistent volume as a storage volume within an EKS pod. In my persistent volume claim definition, I have specified a name for the PVC, the name of the PV that I want this PVC to be bound to. Let's go ahead and apply this persistent volume claim definition. The PVC has been created successfully and is bound to the PV. We are now ready to deploy a pod that uses this PVC. In your pod deployment file, you need to specify the name of the PVC to attach and also the local mount path. In this case, we are mounting the persistent volume claim under /work-dir. Okay, let's deploy the pod. Let's log into the pod. We can see a 1.2 terabyte FSX Veloster file system has been mounted under the /work-dir as per our pod deployment definition. Given we have deployed an FSX Veloster file system that is linked to an S3 bucket, when we perform a list operation on the folder, we are actually seeing what's stored in the S3 bucket through the FSX Veloster file system. Now, how cool is that? Being able to integrate with the data in your S3 bucket without any code. Note that the data will only be pulled into the FSX Veloster file system from the S3 bucket upon first access, where subsequent access to the same data will be served directly from the FSX file system at sub-millisecond latencies. Also, newly written data to the FSX file system can be automatically exported to the S3 bucket based on your configuration. This means that you could have a small 1.2 terabyte FSX instance deployed to act as a high-performance cache to hundreds of terabytes of data stored in Amazon S3 bucket. Now let's test the automatic data export feature of FSX file systems linked to an S3 bucket by creating a new file and verifying it's exported to the linked S3 bucket.
You can see which S3 bucket is linked to your FSx instance by navigating to the Amazon FSx console, selecting your instance, and looking at the Data Repository tab. Now this is the S3 bucket linked to our FSx instance. Let's go check out if the new folder that we created called new data and the file test.txt were exported to this S3 bucket. We can see that both the new folder and the file have been exported to the S3 bucket. Okay, let's recap on what you observed in this demo. We showed you how easy it is to configure and use an Amazon FSx Veloster file system as a persistent volume within your EKS cluster and its deployed pods, where you can deploy an FSx Veloster file system either as a standalone instance or as an S3 linked instance. We also demonstrated how automatic data import and export works for S3 linked FSx Veloster file systems, which is really beneficial for pods that require both high performance storage and S3 data integration.